Alright, good morning. I hope you're staying warm. We're going to start on page 14 of your notes packet. If you do not have your notes packet, it's available for download, the entire packet, at the bottom of the page under Term 2, Unit 3. So please make sure to refer to that if you do not have it. You're welcome to print that to OneNote, or you could print out just these selected pages. It's up to you. Alright, so we're going to start by first taking a look at finding, obviously I didn't have a quiz right now, finding x-intercepts of absolute value functions graphically and algebraically. First we're going to take a look at them graphically. So you'll notice 1, 2, and 3 are asked to identify the x-intercepts of the absolute value function shown on each graph, expressed as an ordered pair. Now there are 3 different situations we can face when finding x-intercepts of absolute value functions. And number 1, you'll notice our graph touches the x-axis one time. So we have one x-intercept of the function described in number 1. So that x-intercept is 2, 0. So that's one possibility. You could have one x-intercept. 2 shows an example where you have 2 x-intercepts, since our absolute value function crosses the x-axis 2 separate times. So in 2, we have the x-intercept -2, 0, and we also have the x-intercept 0, 0. So that's another possibility. You could have 2 x-intercepts. 3 is an example. We'll notice our absolute value function never crosses the x-axis. So we have none or 0 x-intercepts. I prefer if you would write none though. Keep in mind, if you write 0, you are inferencing the point 0, 0. So just avoid any mix up with that by writing none for that one. So we have 3 possible ways, or 3 possible outcomes for the x-intercepts of absolute value functions. You could have 1 solution, 2 solutions, or no solutions. So that's how we can tell graphically how many solutions or x-intercepts we have. Now there is a way to find that algebraically, but before we move on to that, you have a little snippet of solving absolute value equations from what we did in Unit 2, so what your most recent test was on. So we have the example, the absolute value of -2x plus 7 equals 25. First thing you need to do is make sure that absolute value expression is isolated. Here it is. And then you can branch it out. We'll drop the absolute value bars, set that expression -2x plus 7 to positive 25, and then -2x plus 7 equal to -25. And then we would solve. And you see the work there, and you get 2 solutions. So that's the same process we're going to be using to find x-intercepts of absolute value functions. So let's take a look at number 4. For us to find the x-intercepts of absolute value functions and the vertex of each one. Vertex, we'll be using the fact that all these are written in vertex form. Y equals a times the absolute value of x minus h plus k. Keep in mind h is the opposite of what it appears. So number 4, our vertex is 2, -4. We're going to go ahead and do number 5. Our vertex here is 7, 5. Now to find the x-intercepts algebraically, we're going to be substituting in a value in for y. Now let's refer back to 1, 2, and 3, or 1 and 2 especially. You'll notice our y values for all of these x-intercepts is 0. So our x-intercept is the value of x when y is 0. So we're going to be substituting 0 in for y and then solving for x. So for number 4, 0 equals 3 times the absolute value of x minus 2 minus 4. So keep in mind we'll be substituting in 0 in for y for all of these. Now we're going to solve this as an absolute value equation, but as we reminded ourselves in this example, we have to isolate that absolute value expression. So in number 4, we need to isolate the absolute value of x minus 2. So we'll work backwards. Same way we did with solving equations. First thing, we'll add 4 to both sides. So we'll get 4 equals 3 times the absolute value of x minus 2. Once again, we want to isolate that absolute value. Let's divide both sides by 3. So we get 4/3 equals the absolute value of x minus 2. Now we can use our reflexive property to write this as the absolute value of x minus 2 equals 4/3, just so it looks like something we're a little bit more familiar with seeing. And then just as we did in that example worked out, we're going to branch out, drop the absolute value bar, so we'll have x minus 2 equals 4/3, and then x minus 2 equals negative 4/3. So that same process as what we did in Unit 2. The difference is we're going to have to substitute in 0 and for y. And then everything else is the same. Now, as a side note, 4/3 is 1 1/3, and that's going to be a little easier to work with, especially if we're adding 2 to it. So we get x equals 3 1/3. This one as well. So here we'll get x equals 2/3. So here's our two x-intercepts. So we'll express them as ordered pairs. So we have 3 1/3 comma 0, and then 2/3 comma 0. So that's our process of finding the x-intercept of an absolute value function algebraically. Alright, we're going to do the same thing for number 5. And for space, I'm just going to erase. Alright. So 5, we start with the same process. We're substituting 0 in for y. So we'll get 0 equals the absolute value of x minus 7 plus 5. Once again, we have to make sure we isolate that absolute value expression before we do anything else. So make sure we isolate the x minus 4. So to do that, we'll subtract 5 from both sides. So we'll get negative 5 equals the absolute value of x minus 7. Once again, I'm going to use the reflexive property to write this as the absolute value of x minus 7 equals negative 5. And then we have an interesting issue here. When we take the absolute value of any expression, it's going to equal a positive number, not a negative number. So if you get an equation where the absolute value expression is isolated and it equals a negative number, you automatically know there's no solution. This is a special type that we took a look at. So when this happens, you do not have x-intercepts and you're done with it. So once you isolate the absolute value expression and if it equals a negative number, automatically thinking, alright, no solution, there's no x-intercept. So if we were to graph this absolute value function, it would look like something similar to number 3, where the absolute value bar, or the absolute value function, doesn't cross the x-axis. And that makes sense if we think about this one. This one, we have a horizontal shift to the right 7 units, and we go up 5 units, and it's opening upward. So on a coordinate plane, looks something similar to this graph. It doesn't cross the x-axis at all, so we don't have a solution here. So that's what we're looking at. And then you're just done. Don't put that one. So you can move on. Alright, so let's take a look at that next page. So we're going to finish with number 6. So the same process, we're going to substitute, well, we can go ahead and identify our vertex here. 0, 22. Keep in mind vertex is an ordered pair. That's the most common mistake I'll see. Don't put parentheses around it. It is an ordered pair. We have to put parentheses around it. So to find the x-intercept, we'll substitute 0 in for y. So we'll get 0 equals negative 11 over 6 times the absolute value of x plus 22. Subtract 22 from both sides. So we get negative 22 equals negative 11 over 6 times the absolute value of x. Now here it appears to be, oh wait, it equals a negative number. But we haven't fully isolated yet. We need to move that negative 11 over 6. So we're not fully done yet. So we're going to multiply by the multiplicative inverse. So we're going to multiply both sides by negative 6 over 11. And that will divide out with the negative 11 over 6. So it's going to equal the absolute value of x. And negative times a negative is positive. 11 goes into 22. There's their GC over 11 2 times. So we'll get 12. So get the absolute value of x equals 12. So keep in mind, even though it appears to equal negative, you can't rule that out and say there's no x-intercept until you fully isolate that absolute value expression. Excuse me. So we have the absolute value of x equals 12. Remove the absolute value bars, set it equal to the positive, the given one, and then the negative value. So our x-intercepts here are 12, 0, and negative 12, 0. So that's what we're looking at with finding the x-intercept algebraically. Alright, I want you to complete for homework 7, 8, 9, 10, and 11. So you're going to just finish up this page. We'll take a look at it on Monday. Stay warm.